So today we talk about Pozzolanic and hydration kinetics. Yeah, we are really going into the fundamentals. So that's why we are using, C3S hydration, but I also try to put some examples like we had with the metakaolin, so that keeps it more, realistic for the current challenges, to make it more close to the problems that you research nowadays. Yes. So we will continue with cement hydration kinetics of the C3S, but the same theory you can apply to any kind of system. I use C3S because it's well known, so it's easy to understand. And this is the outline of the first hour. So it's about the cement hydration kinetics. So the reaction of cement with water, stoichiometry and volumes, this is what we already did yesterday of C3S. I will explain a little bit more on the solid volume increase, because if we have particle-based models, this is the microstructural model, then we also need to calculate, the volume, the solid volume increase, how the particle then grows. So we can model the cement hydration kinetics. I will show you an overview of the models, which models are available, what are the main mechanisms, like, the nucleation and growth, dissolution, nucleation and growth and diffusion. And I will show it on the single particle. And then comparing different model methodologies, also the most advanced, most fundamental model from EPFL, I think, from Scrivener group, which is on C3S cement, only C3S allied clinker. And then I will finalize with multi-particles. So when you have a lot of particles, then you have, the overlap. Each particle grows and the hydration shells, they overlap. So you need to consider this volume balance of overlapping spheres. And this is the Heimerstruck model, which was developed in TU Delft, which I also contributed, and Professor Kunders was the main, behind the Heimerstruck model. Actually was from Van Breugel, which was the mentor from Kunders, but he did statistical model. So that time in 80s, when the model was first made, there was not so much computational power, so it was only statistical based model, which was actually very clever, very smart model. And nowadays they still apply this approach again on the Mike model. They also used it, but actually the first idea was from Heimerstruck, from Professor Van Breugel from TU Delft. But later, 10 years later, we have the full power of the computational power, so we could really, computationally simulate each single particle in a 3D system, like a virtual growth of the particles. So this is what Professor Kunders did, and I also then extended for the Pozzolanic reactions, and I did diffusion models through such virtual microstructures. So I will explain you the basic rate equation of Heimerstruck. Today this model is outdated because basically it lacked nucleation and growth, which is the most fundamental mechanism for the cement hydration. This is shown by Scrivener, and but this is also what I tried in a simplified way, how to model nucleation growth also in Heimerstruck. So you will get a nice overview of hydration model, kinetics model, what are the available models, which is the most state-of-the-art in literature models, what are pros and cons, and yeah, so you can have a nice overview of the hydration kinetics modeling. So this is the sphere. We have a gray, this is the initial cement, the red part is the reacted part. So it's a shrinking core, growing sphere, growing shell, we could call it. So the red part, initially the red part, there is only gray part, which also covers the red part. So the red part actually shows you how much it is consumed. This is the cement which is consumed. It is also filled with the inner CSH gel, and the yellow part is the outer shell. So this is the growing shell, which is because the volume of the CSH is bigger, lower density than the cement. So that's why we have this volume expansion. And this is the multi-full, the Heimerstruck. When you run the Heimerstruck, you will get something like this, which is you have the full particle size distribution effects. So the smaller particles, they hydrate faster. They are almost completely hydrated in the beginning if they are very small, and the bigger particles, they react slower. I mean, the individual degree of reaction you have. So you will see that you have actually now to calculate all these properties, degree of reaction per each fraction. So per each size fraction, you have to calculate the degree of reaction and then sum it up, and then you get the total overall degree of reaction. So this you know from yesterday. If you want to practice, we can even draw, if you want, the monocarbonate reaction, just to remind you what we did yesterday. So if the monocarbonate, and how you can simply actually do these mass balances. So if you want to do it for monocarbonate, let's say, let's write here. Let me clean this. So we are doing the AFM, it's called AFM, aluminoferrate mono. It's an anionic clay. Clays have, you know, the interlayers and cations inside. And these are called anionic clays because they also have double layer, aluminate and silicate layer, and inside is they have anions interlayer. That's why they are called also anionic clays. And yeah, the interlayer, in the interlayer you have the calcium, you have the carbonate CO2. So this is the monocarbonate. So if this is inside the interlayer, then we have the water here. We have the C3A. Yeah, and it's also 3 times C3A. So this is how you would write this reaction. So we have the C3A here reacting plus calcium carbonate, because yesterday we had gypsum. Now we want to see if you have calcium carbonate, and then we just have some water. And now we know that we need to balance it. So we have the, how do we balance it? So now it's the equation for making the balancing. So we have how many calcium we have here? 3 times 3 is 9, 1 is 10. So we have 10 calcium oxides. And if you put just 3 here, yeah, it's simple. Then we have the same. Yeah, it's very simple actually. So this is the reaction. C3A plus calcium carbonate gives you the monocarbonate. You have also hemicarbonate, these different types of interlayers. So yeah, and all these reactions then give you the, you know, the volume expansion. This is why the cement sets also, because you have an increase in volume of the solids, and then you know, you have less and less porosity. That's what the concrete also hardens. and has a compressive strength. So we can continue. We also learned yesterday that actually everything goes through the solution. So you have these dissolution constants, and also you have precipitation constants, and this is a dissolution precipitation reaction. But if you want to simplify it, you can only take the solids and see the also already calculate the stoichiometry. But you should remember that actually, if you want to really go into the fundamentals of the reaction, because the rate of this reaction depends how far these ions are from the equilibrium. So if you really want to model the fundamental kinetics, you should couple it to the thermodynamic models, and that the rate is a function of how far you are from the equilibrium. So then you need to know the concentration, the ion activity product, which is the sum of all the ions which are involved in this precipitation reaction. Not the sum, the multiplication of the concentrations, but also on the power of the stoichiometric coefficients. And then you have the, then you know the driving force for how fast the reaction should go. And the more you are close to the equilibrium, the slower the reaction. And if you are in at equilibrium, the reaction rate is 0. So this would be the most fundamental kinetics, that you should couple it with the thermodynamics, because the main driving force is how far you are from the equilibrium. Same for the dissolution. So basically it's the interplay between the dissolution and precipitation, and the concentrations are actually telling you how far should the dissolution, and then how fast is the precipitation. Okay, so now back to simplified model. We can just also calculate the stoichiometry, because for now we just want to know the the volume growth. Let me just how to go back. Like this. Okay. So here you can see the video of the Heimerstruck model. If you would run it, you would see how these particles are placed in the box. So first you need to place particles, cement particles in the box, and then without overlapping, and then run the growing algorithm. And for this you need to know what is the mu factor, and mu factor is the expansion, how much the volume of the hydration product is bigger than the volume of the of cement. So this is the volume of the hydration products. That's why we have the sum of all the hydration products. So the molar volume of the, because again you need to work with moles. So the molar volume multiplied by the stoichiometric coefficient of all the of CSH and Portlandite, all the hydration products. We have the sum of all the hydration products here divided by the molar volume of the cement, gives you the expansion factor, how much the solid volume of the hydration products for the full reaction is bigger than the volume of initial cement. And this is usually around 2.3. So for C3S 2.3, so you have 2.3 times bigger volume of hydration products than the volume of initial cement particles. This is because of the difference in the densities. Yeah, you can also see, because this is the solid, then we can also see how the pore volume is decreasing. And what I did in Delft is I then calculated the diffusivity through these pore networks, how the diffusion model would work. So we have here, for example, chlorides, or you can see how they penetrate this kind of structure. And you can then consider capillary pores, but also the CSH pores. But I will talk about these diffusivity models more on Thursday. Yes, is the durability. So there is, yeah, of course, a clear link between the reactivity, hydration models, chemistry, and diffusivity, because the final microstructure basically determines the diffusion properties, which then determines the durability. And to have the final structure, you have, if you have slow reacting Pozzolans, then this is always ongoing reaction. Then you have also the change in the microstructure properties. So it's always connected, the hydration with durability. Actually, we need to solve both together. And yeah, I will talk about it more tomorrow, but now let's focus back to our volumes. So how do we calculate now the volume of our growing shell? We just need a volume, the mathematical description of the sphere. This is the volume of a sphere. 4,3 pi, the radius on the third potential. This is the volume of the initial sphere. This is gray. At the beginning, everything is gray. Also, the red part is gray, and there is no yellow part. But we want to calculate the outer shell, and the outer shell is actually the total volume minus the initial volume. So it's just the yellow part. The yellow is the total minus the initial, and initial is the gray, which was initially the red was also the gray. So the outer shell is then calculated as the outer radius, which is the total volume, minus the initial radius. So this is how you calculate. Then you get also the outer radius. You can then calculate the outer radius. You just take out this and explicitly write it as a function of the volume. So this is what you want to know. You want to know the XYZ positions of all the particles. You know the radius of each particles, and now you want to know during the growing algorithm, you want to know the radius of the outer shell. And then you can do this simulation in full 3D. But to know the volume of the outer shell, you actually basically need the initial volume and the expansion factor, which was 2.3 when you calculate it here. So this is how you can then plug in here, and then you can easily calculate the radius. But this one we also want to know as a degree of reaction, so that's why we just multiply by the alpha, and this is the degree of reaction. So very simple sphere-based model. The only complicated part is to do it for all the particles, which is also very easy nowadays with the computers. But you need to just to take care of the volume balance. So you need to take care of the overlaps of each particle. And then because if you have another particle here, they are overlapping. And that overlap should be, you need to increase the particle. Each time they overlap, the amount of overlap, you should increase both particles which are overlapping. And then you have a more overlap. So you again need to increase, but luckily this is converging. And then finally you can calculate the volume, that the sum of the total volume should be respected, that you don't lose any volume or you don't create additional volumes because of this overlap. So there is an overlap algorithm was made also by Eddy and by Van Breugel in statistical approach, and actually it converges, so it's possible to do this overlap algorithm. Yeah, this is for the water. This is what we did yesterday. No need to explain further. Here I just did it explicitly for you, how you can calculate it, and you get the expansion factor with 2.3. So the molar volume is molar mass divided by the density. So you just have the ratio of the molar masses, the density, and the stoichiometric coefficients. And when you sum this all up, you will get the value of 2.3. Mostly comes from the CSH because it's there is a bigger portion of CSH and also I think less density. So the total volume factor is 2.3. So the hydration products have 2.3 times bigger volume than the initial cement, if you consider only C3S reaction. So this is what I just explained. Yeah, any questions here? So with this now you can implement already your, at least we will do this for a single particle in a Python example. And now I will go to the second topic. This is the chemical kinetics. So what is chemical kinetics? It tells you how fast is the reaction. So if you have, you know, just in a solution, how fast the reactant is consumed, or how fast you have the production of a compound B. So this is if you have a reaction A goes to B, then this would be the concentration, how fast this concentration is consumed, the rate of conversion of A, and this would be the rate of production of B. And this rate is usually mostly just if it's in a solution, the rate would be K times the concentration of, depends what you want to, yeah, basically it's the rate times the concentration of A, for example, if we look at the consumption of A. So the more A you have, the higher the concentration. The higher the rate, I mean, the higher the concentration and the higher the rate. This we know from the, you know, from the COVID, from the virus spread. The higher the concentration of infected people, the higher the spread of the virus. So it's the same principle. You could using this kind of kinetics law, you could calculate the spread of virus. So this, we have the how the concentration, and this is when you solve it, because this is actually a differential equation. Just let me write it. The rate is the, you can see it here, is the change. It's actually the slope of the concentration here. It's this slope, and if you solve the differential equation, you actually get exponential solution. So this rate is the slope. We can see it here. But if we have intimenzimally, the rate is actually dA dt. So this is the rate, and this is exactly the slope here. Is this slope? This one, the slope. So in terms of energy, because the concentration is energy, the higher the concentration, the higher the energy. You remember yesterday we had this Gibbs energy is Rn RT ln concentration. So there is a relation between energy and concentration. You just need the Boltzmann constant and the gas constant, the R. Yeah, basically it's the Boltzmann constant which is basically also the Avogadro number. And you need the temperature. So you just need concentration, temperature, and that's you get the energy. You can calculate the energy. And you have, if we have now reaction A plus B, and then gives you C, we know by thermodynamics, we only know the initial and the final point, and this reaction will be, if this change in energy, which is the Gibbs energy, is lower, then we have a spontaneous reaction. This reaction will happen if the products are bigger. So that means that the delta G is bigger than 0. The change is up here. Then this reaction is not spontaneous. It will not happen. So only spontaneous reactions happen. And you know, if you will burn cement, you have very high energy inside the cement, and this is why that reaction is spontaneous. It's also very exothermic. So that's just by thermodynamics, it's just equilibrium. But where now kinetics comes into play is actually the kinetics is this hill, because the atoms have to hit each other. And only the atoms that have enough energy to overcome this barrier, they will react. So not atoms have enough energy when they collide to react. Only certain amount of atoms with high energy, and we have a distribution of energy of the, how the atoms are moving. We have this Brownian motion. So only a certain amount of atoms that can pass this barrier, they can react. And this actually determines the reaction rate, because we have this energy barrier, and we can, if you use catalyst, you can reduce this energy barrier. But basically this energy barrier is, you always need to go up and down, up the hill, and how high you should go to form, to overcome this energy barrier. This is basically determining the reaction rates. And you can measure very simply the reaction rate of the cement hydration by isothermal reaction calorimeter. You can have this, TAM air, or we have this other type of calorimeter from Germany. And but basically, yeah, you just make cement paste, fill it in. You have inside the thermocouples, which measure the temperature difference. And from the temperature difference, you know the flux. You keep your sample isothermal. And from the flux, which is the heat flux, it's the milliwatts. So it's joule per second. That's the flux. You know how much energy was released. And this is a typical hydration curve with time. So you can see with different temperatures how the rates are increasing. The hydration rate is increasing. And now if you would integrate this curve, so this is a differential curve, these are the rates. If you integrate these rates, you get the heat evolution. So you get the integral curve, which gives you the total amount of heat at each time. And now to go to the kinetics, I will explain what you should actually do, how to transform these kind of curves to get kinetic curve. And this is actually for aluminate cements I did in my PhD. And then if you transform it in this kind of degree of reaction, the rate as a function of degree of reaction, you actually should get, like a master curve. And then you can calculate the activation energy. So here they look, they look shifted in a way, but because the time is not the real state parameter that defines the better parameter to get the master curve is the degree of reaction, and then you will get, that all the curves are aligned. They are just multiplied by some factor, and this is exactly the activation energy. this curve is a little bit shifted, and this shows you that you have a different reaction mechanism. And in aluminate cement, this is forming metastable hydration products, which are different than here we have the CaH10, and here we have the anionic clay. So here we have, if you have the same reaction, you will have the master curve, which you just have to multiply by some number, and you will get here the same. You will get like a master curve, and then you can calculate the activation energy. So how to get this curve? So you actually need to, so if you have this delta Q dt, so this is the flux. That's what you have here, milliwatts per gram. It's always per gram, but let's just say it's the total energy divided by time. So it's the differential. So you need to actually divide this by the total heat. If you divide by total heat, which is here, if you extrapolate, you would get here a value which is Q tot. And then with this, or you can just take the final value, then it's, you can say this is the my Q tot, but then you should remember that your degree of reaction is not, it's just not the real final degree of reaction. And then you basically get, you get, because the Q, this is in time, in every time, and this is the final point, you will basically get the alpha dt. Because the alpha, if you know alpha, the degree of reaction, we call it before degree of reaction, now we have alpha also, just simpler. And the degree of reaction is defined actually as Q in time t divided by total Q. So this is how you can calculate the heat in each of these points. In every point, if you divide this every point by the total Q, you will get the degree of reaction. This is just a simple way how you can calculate the degree of reaction. And then you can, this is what you can then plot here. This is the degree of reaction. And here you have this d alpha dt. This is the rate. So basically, it's the rate as a function of the degree of reaction. Let's call it alpha now. And then you get this kind of curves, master curves. Yeah, it's always, after measuring, you always need to do some, you know, mathematics to get some data from the measurements, from the raw measurements. You need to, you know, analyze the raw measurements. And then you end up actually doing modeling. So this is now which models then you can use for this d alpha dt as a function of alpha. So you can use, this is the most simple autocatalytic kinetic. It's an empirical equation that gives you this shape of the curve already. Because we have alpha degree of reaction multiplied by the of unreacted, and then it goes alpha goes up and minus alpha, 1 minus alpha goes down, and then you will get this bell shape of the curve. This surface area could be, and this is just the parameter k. So this is the most simple equation, but of course this would not really, it's actually symmetric. You would get a symmetric curve, so you cannot really fit this shape for cement hydration, because this with nucleation and growth we actually have a higher rate. You could try to do some exponents here, and this is, you can all find this in chemistry. This kind of simple. This is the most simple kinetics. If you have, you know, like it goes up and down the rate, but yeah, we need more fundamental reaction rates. And this is what I did for my PhD in for aluminate cement. I basically split it to model the nucleation and growth. Very simple, actually, model. So I just said that this is nucleation and growth. It's just linear growth. Very simple linear equation. The rate is equal to the constant of the nucleation and growth multiplied by the degree of reaction. I have also here a shift, because you can see there is a shift. This is just because of the setting time. Then I have the interaction. This is the cement reacting with water. So I have the degree of reaction of cement, degree of reaction of water. It's a bimolecular reaction. Because you remember, the reaction rate is K times the concentration. But now we have the concentration of cement and concentration of water. So this is how you would write chemical reaction rate, how the chemist would write the reaction rate if you have it in solution. But of course we have particles, so we also need to add the diffusion. But basically the reaction rate of the interaction of the cement and water is just proportional to the amount of cement, which is 1 minus the degree of reaction. This gives you the amount of unreacted cement. Basically, is the concentration of cement. And this is the amount of available water. And this is the concentration of water remaining. And basically, it's 1 minus the degree of reaction of water. And I put it here on some exponent just to get more this shape of the curve. So this is how I model the interaction. Basically, it's this curve. And then I introduced diffusion, because it stopped at 0.7. If you would continue, this would stop at 1. But I wanted to make it stop earlier. And this is because of the diffusion. And I just introduced the mass transfer coefficient, which is again proportional to the unreacted cement, amount of unreacted cement, and divided by some factor eta, just to control this when it stops. And then I summed it all up, but not because, you know, it's always one. There is always one mechanism that is governing the rate. So it's called, in the kinetics, this is called the rate determining process or rate determining mechanism. So at the beginning, this is nucleation and growth. Maybe fully at the beginning is dissolution, but I didn't consider dissolution here. I just modeled from nucleation and growth. So in this part, the rate determining mechanism is nucleation and growth. Then we have the interaction reaction between cement and water, where the amounts determine the rate. So the amount of water in this case mostly, because the water is what is usually consumed first. And then we have the diffusion, which is determining the rate. And then you can, but I did a harmonic mean of this. So I just did, which is actually the mechanisms are run in parallel. So if you have a harmonic mean, you would write that 1 divided by 1 divided by the rate. This is how you determine the resistance, you know, of the parallel resistors. So the resistance of parallel resistors, you just use the harmonic mean, and this is exactly what I did. So it's like from electrotechnics, if you remember the resistor of the parallel series. Yeah, maybe let me write it, then you will get what I am talking about. So it's just, you know, if you have, there are two two ways of how to do it. So the rate, you can think of the rates as the resistors. This is a series. This is approach which was done in literature. So this is the rate number 1, this is the rate number 2, this is the rate number 3, and you can put them in series. And then if this is the highest rate, this will determine the whole process. But I didn't do it in series, I did it in parallel. So if I put the resistors in parallel, and then I calculated the total resistance is the, you know, this law, the sum of reciprocal value of the sum of all reciprocal resistors. This is the harmonic mean. And then I calculated the overall resistance, which is basically the overall rate. Yeah, recently I had a PhD student. She finished 2024. And we had this publication in Materials and Design where we actually applied the same kinetics, similar kinetics on the modeling pozzolanic reaction of metakaolinite, so aluminate silicates. This is the R3 test, and if you mix metakaolinite with portlandite, you get you know, the exothermic heat, so you can measure the heat flow. And what she found out, we also measured very early reactions. We developed new methodology how you can also measure early reactions in heat calorimetry. Usually R3 test is by 40 degrees, and you need to mix it, you know, outside and then put it inside. But we made a method how you could also measure it from very early. And she found basically that, you know, within half a day there is first reaction and then there is a second reaction. And then she was very interested. Okay, what is the first reaction? What is the second? And actually the first reaction is the formation of these calcium aluminates. And the second one is the stratengite. And this is what we balanced also yesterday. And this also doesn't involve sulfates, but in cement you always have sulfates. So actually you can do similar on sulfates and carbonates. But I think Zunino from Scrivener, he did already a lot of tests on that. This is why she mostly focused on without sulfates. Makes life easier also. And yeah, she also developed the model, and she followed how this model was written in MATLAB. So just based on the stoichiometry and these kinetics, she could predict the development of all the phases, how much metakaolin reacts. Metakaolin is here. How much portlandite reacts, and how many phases are forming. And she validated this by XRD, Rietveld refinement, and TGA measurements. I think those are mostly from XRD. And we did also EDS, chemical composition. And but the same, yeah, she used the same model basically, but now split it in from 2 peaks. So we had to split these 2 peaks into individual peaks and the degree of reactions of the individual reactions and do the total reaction. So this is, you can see the details in this paper. So now I will talk about the history and main models for the kinetic models for cement hydration. Actually, everything happened, started in 1980 by Beziak. He published a paper in CCR. And actually, Beziak was, I met him. He was in my same university where I got my PhD, in University of Zagreb in Croatia. And he was already in, you know, retired, but I met him. He was in the same group where I did my PhD. So he's the first guy who started with particle-based models on cement. And yeah, he did for C3S, and these were the models. Basically, he took Avrami Erofeev model for nucleation and growth. So this is a particle-based model, fundamental model. You can write it as a function of time, but you can also find it as a function of degree of reaction. This is also from Croatia. One scientist who did it like this, but he made, you can see here, he made the total. He modeled nucleation and growth, then he modeled the interface, and then he modeled the diffusion, and he said that the rate is equal to the rate determining process. So this is even not in series, this is just individual, and if this is higher, the rate is determining, it means it's actually lower, then it's equal to this rate. That's why you have this, you know, like crossings. The function is not smooth. And this approach is also parrot and kilo approach. He basically extended the approach from Beziak and extended it to four clinker phases, and he added also the effects of the water cement ratio and relative humidity. And this is the approach you see in GEMS. So this is what Barbara Lottenbach is using. And yeah, beside the nucleation and growth, you have also the interaction. You already saw it with me, with the power of 2, because you have the, you know, cement and water, but I modeled this separately, which is better because then you don't have to add water cement ratio in an empirical way. And here is the diffusion reaction, which is basically Yander diffusion. But the Yander diffusion actually doesn't consider the shell, it only considers the growing, the shrinking core. And the right model actually would be Ginsling-Braunstein model. This is N at the end, Braunstein. And he also developed further this Yander model that considers also the growing shell. So you have increasing the thickness of the diffusion. So this should be the right model. The Yander is not the good model, actually. I will show it later. So now I will continue. This is the state-of-the-art model from the Scrivener group, Karen Scrivener from EPFL, from Lausanne. And this is a PhD from Ozia. And he did the nucleation and growth model on the C3S hydration, mostly experimentally, but also he developed this kind of model, which is parameters are mostly based on the experiments. He measured the rates, very tedious work bits with microscopy. So he followed all the, you know, hydration products by microscopy and how much of that hydration products is developing during time, and then based on the particle size distribution of C3S and shape from the laser granulometry and again microscopy. So basically it's a microscopy, a lot of microscopy images with time that gave him insight into this model. And they basically say that the whole process is determined by nucleation and growth. So the first model you saw, they say that it's the diffusion. Now they say, no, there is no diffusion, everything is nucleation and growth. But actually there is even a third school. They say everything is dissolution. I didn't put this model here, but it's from from France. Nicolas. And he actually argues that the whole process is governed by the dissolution of clinker. And then because you have the saturation, and then this, how far is it from the equilibrium, the whole thing is actually governed by the dissolution. But here they actually somehow proved that it's also nucleation and growth. And we have this deceleration, the peak is coming because those CSH crystals which grow on the surface are actually becoming saturated. There is no more, you know, space to nucleate more of these cylinders and grow. And this is why the nucleation and growth starts to decline, because of this lack of growing space. So this is how they explain it, and you can see here the rate, the nucleation rate, and then it's just forming new cylinders, new needles of CSH, and then later they grow. This is the growth mechanism, and they have actually developed this model. This is the heat flux, the enthalpy. There is the molar mass, the surface area, and then we have this function, and this function of the kinetic function they got from the microscopy, which basically they got these kind of functions. And they really proved with with zinc, if you have C3S paste with mixed with zinc, then you don't have you have actually let me see, you have retardation. You have a strong retardation if you use zinc, but you have still increase in the peak. And this can only be possible if you can explain it with this kind of mechanism. You can find more details in this paper, and there is one more paper from Scrivener. I think I cited it later, where she makes like a review of this of the hydration models. But I would argue that there is always diffusion, of course, because even the solution has a diffusion, and the precipitation has a diffusion, because you have here, if this is a cement surface, you have the CSH, inner CSH, outer CSH, lower density. You always have concentration gradients. You also have the saturation indexes. And the outer, of course, is less saturated index than inside. So here you would have more driving force for precipitating than outer. And actually, Zayats from Heidelberg Cement, the group, they measured the ion concentration in the C2S hydration, and they showed that actually when you measure the ion concentration, you could see the saturation indexes, and for dissolution means that the saturation index is smaller than 0. Then you have the dissolution reaction, and you can see actually that initially you don't have the dissolution, you only have it later, because it's super saturated initially, and then later it gets undersaturated, so you can dissolve. And for the CSH, you actually have, yes, the saturation index is bigger than 0, and that means that you have precipitation. And this is the kinetic load, and would be the the surface area and the kinetic parameter, and how far are you from the saturation index. So how far are you from the equilibrium? And here is the concentration of some activity of accelerating or retarding species, for example, pH. This could be pH. But most important, yeah, you need to relate it to the thermodynamics. How far are you from the equilibrium? Yeah, these kind of models are actually still missing for cement hydration. There are maybe some models also here from Germany, from Erlangen, from Neubauer professor, and they did one PhD, but only on C3S hydration. Again, these kind of models. But for cement hydration, those models are still missing actually. So now that gives us yesterday you looked at CEM-GAMS app, and you saw these kind of predictions, and they are actually using Parrot Kilot kinetic model. So this is based on nucleation and growth, diffusion, and hydration shell. And only they are actually The one that has the highest rate, that one is no, the lowest rate, sorry. The one that has the lowest rate is the rate limiting. Yeah, actually it is the highest rate. Oh, sorry. It is the highest rate, the lowest resistance, I mean. That is the rate limiting process, and then you only take this function. So it's actually following this kind of approach. That only the one reaction, which is the main, the highest rate, that is determining the overall rate. So this is what it's implemented in what Barbara Lottenbach implemented in games like 10 years ago in her papers, and now it's implemented also in this same games app. There are also other models you can use, but they are all actually empirical models, just fitting the shape of the, you know, this exponential shape of the degree of reaction. Here we have some factors. This is what is for the water content, surface area, and also temperature. So the Arrhenius, this is the Arrhenius function, how the rate changes with with temperature. We have the water effect. So at the end, you can to calculate this, you need to, you know, solve this differential equation, ordinary differential equation, and you can use simple finite difference method. And this is what I will show you, how you can implement this in the, so you can implement it in a Python code. So to sum up, we have, I have showed you the overview of semi-hydration kinetics. I showed you, you can use simple empirical models, which are basically curve fitting approach. They are data-based, so they have low predictability. That means you cannot extrapolate them, and they are valid for the systems you fitted them. But if you have a new system, it will not be, you cannot extend them. That means that there is not, extrapolation is not possible. That's in general why you should not use empirical models. But of course, if there are if the fundamental models are too complex or valid only for, you know, simple systems, then you should use empirical models, this engineering approach. But you should be aware that this is a curve fitting approach and you don't have extrapolation ability. Actually, this is true for all machine learning models. But then you try just to, you know, learn and put some data that the machine didn't see, and then you are like, but yeah, actually you don't have extrapolation ability of any machine learner. You need to have, you know, physics-based models to be able to extrapolate, to predict data which are not used for training, let's say. Then I showed you the mechanisms of the kinetic. So we have the nucleation and growth, dissolution, reaction, interaction between salmon and water, and we have the diffusion. Those are the mechanisms, and each mechanism in each stage can determine the rate. You can then put them in series, so they are the rate controlling, or you could actually, and those mechanisms actually I showed you, those are fundamental equations for the particle growth, but then you should also put the particle size distribution, which is the Heimerstruck model basically, to calculate the overall rate. This is what Bezek also did in his first model. He did it for full particle size distribution. And I also proposed the, you know, more gradual shift between these mechanisms, and this is the parallel process. This is what I proposed in my thesis. So then I showed you also advanced microstructural models, which actually, like Heimerstruck or Mike, which basically have a lack in resolution and computational power limit to go really fundamentally. But Mike would be such a fundamental models. And then I showed you more advanced models, but they are only for C3S. Basically, they only consider nucleation and growth. and they are not yet applicable for cement. So this is still research to be done to apply it for cement. So with this, I can continue now with to show you the Heimerstruck model. So this is the Heimerstruck model, microstructure model. This is from Van Breukelen, from TU Delft, the original idea, where you have the expansion algorithm, how it works. So each particle expanding, and then because it expands, it overlaps with other particles. So you need to consider this volume balance. So you should expand a little bit more, not to respect the volume. And then you iterate this kind of algorithm. You need to calculate how much you have the overlaps, and this volume which you overlap, you should add to this central particle to expand further. And then you again overlap a little bit here. So you again add, and this is converging, and then you can run this algorithm. This was done in the 80s by Van Breukelen in the statistical way. And later Professor Kunders, he did it in the full 3D particle-based model. And then if you calculate, you will see that these particles actually, each particle has a per fraction. You can calculate the degree of hydration. For example, particles which are only 2 micrometer, they react, consume very fast. In 10 hours, you consume all the small particles, but the bigger ones, the degree of reaction of the bigger ones is smaller because you have, the effect of the sphere, and also the diffusion is bigger. So this is the basic rate equation in Heimerstruck. And basically it's again, you see this the differential equation, which when you integrate, it becomes the, finite difference method. So you can calculate this is delta in is how much of the cement is consumed. This tells you the thickness of the red part. Delta in is the thickness of the red shell. It basically tells you how much of the cement was consumed, and you want to know the thickness of the red shell for each particle, and this is equal to the constant. So this is actually it's the dissolution rate constant. So the Heimerstruck only modeled dissolution, and then the effect of the diffusion, which is here, and then the effect of the water and microstructure and distribution. I will explain all this. And these are nowadays the models also from Scrivener. They also go back to this, but of course they don't cite this paper. They just reinvent again the same thing. Because it's important, but they just say it's the new thing, which is not the nice way to do, of course. You should always credit the original ideas. And let me explain. So this is the rate factor is the dissolution part, and this part is the diffusion, and basically it tells you have this phase boundary lambda, and if this is 0, then you don't have this term. It's very engineering, very nice actually engineering model. So when lambda is 0, you don't have diffusion. This is the threshold thickness. Maybe I should have a, let me draw it. No, not this one. Let me draw the particle. So if this is the particle, we want a nice sphere. Difficult to draw. Let's say this is a sphere, and then we have this, the inner part. So this thickness, how much it goes inside, this is the delta in, and it's per particle. So this is now particle I, let's say, and then you have the outer shell. And then when you reach certain thickness of the outer shell threshold, this is the threshold, then you enter the diffusion mode, because you know there is a certain thickness of the shell that then starts the diffusion, and you define this thickness here. So this is the transition time to diffusion limit. So basically you transition from the solution into the diffusion limit. You also need nucleation, otherwise you don't get, you know, the curve going up. You directly, basically the original Heimerstruck model is if you have the delta, let's call it delta alpha, delta t, just, but here this is related to alpha. You will see later how, just based on the sphere geometry. And if you have here alpha, you know, you want to have a curve like this. But the Heimerstruck actually in this way, because this is basically the solution. This is this part is diffusion. So basically you have directly very high rate, and then you enter the diffusion. So this is the model from Heimerstruck, because the way it was meant to simulate was not to simulate early hydration, it was meant to simulate, you know, 28 days and later. This is why it was like this. So here, and what I did, I just said I just introduced the nucleation and growth to be able to simulate also initial reaction. And I just said that the initial, yeah, we just needed to introduce, you know, sometimes you just need to be creative, and simple ideas are always the best. You just need to, I just created that this K is proportional, which I already did in my PhD, that the key, this K 0 is proportional to nucleation and growth as a function of 1 minus degree of reaction. And then I got this line here. Actually, I think I did it as a function of degree of reaction, exactly. So you get this here, and then you can also model then you get this kind of shape again. Let me, okay, so we are here. So we need to have certain thickness to enter the diffusion. So when you, so if the shell thickness is equal to the threshold thickness, few micrometer, then you enter diffusion mode, and then this lambda becomes 1 or -1 actually. It depends how you write it. And then you enter, then this factor is activated. So then you are reducing the initial rate with this ratio of what is the thickness of the shell to the threshold thickness. So the further away you are for the threshold thickness, the more you are reducing. And I think this is -1, so it's actually inverse. So basically you get a factor here which is smaller than 1. If this is threshold thickness, then it will be 1. And the further away you are from threshold, you get a value below 1, because this is -1. And then you basically have a factor which you are reducing the diffusion. And this is actually, it is diffusion. When you model, if you go back to the theory of diffusion, which I showed here, you will see that if it's a flat reaction front, okay, these are for the sphere. But the assumption was it's a flat reaction front because it's an engineering model. So you can correct it for, you know, for a sphere, but there are so many parameters which are, you know, simplified. So you can use flat reaction front simplification, and you will see this flat reaction front actually goes with K divided by the diffusion depth. So this is exactly the diffusion model for flat reaction front. This is why diffusion also looks like, you know, square root law. And this is exactly what is implemented in Heimerstruck. You have this diffusion-based model here for the flat surface. So if you have zero, you have the phase boundary, which is this dissolution, and when the threshold is reached, you enter the diffusion mode, and the further away the thickness, the thicker the thickness of the shell, the more you reduce actually the rate. Here you also have the Arrhenius, and this is the equation I took in Octave, which is actually now in Python. So this is what we can. This is the part we can model in Python in the later in the tutorial. I will explain this later in the tutorial. Yeah, now I will explain the factors. So one of these F is the Arrhenius temperature. So it's just exponential with the temperature difference, famous Arrhenius equation. Then here we have the effect of the pore structure. I will explain it later, but now we also have the consumption of water, because the more water you consume, the lower the rate. It's just the, like the concentration of water. I will show you also how this is implemented. Then we have the amount of water present and the distribution of water. There is a difference between these two. Actually, I don't have these slides. Okay, so it's yeah, you should you can see it in the, actually this is a thesis from Van Bruegel. You can see it in this reference, yes. So basically, yeah, you want to model the total amount of water consumed. You want to model the amount of water present around each particle, because the bigger particles, consume more water than the smaller. So it's also the matter where and how many particles are embedded in the bigger particles. So how many of these particles are embedded in the shell? So they also consume water. So this is why we have 2 times the amount of water. This is on the global level, and this is on the particle level. How much of the water is consumed by the other particles, of the neighbor particles. And this is the distribution of water, which is basically the, also the pore size distribution effect. That the water is present in the smaller pores and the bigger pores are empty. We have this chemical shrinkage and the empty pores. And we have the effect of the pore structure, because basically it affects also the distribution of water. So this gives you the full, then if you would add here nucleation and growth, actually it gives you fundamental kinetics for the hydration of cement, which nowadays more and more people are basically going back to this model, although it's outdated and old, but basically you just need the nucleation and growth. It's still a very relevant model, I would say. And I see this because more and more people start to use same approaches, because all these factors are actually very important. How much water you have. You will see these models also in recent literature going back, but don't citing this paper. So that was it. I think we are 12:40, so we are we have before lunch. We have half an hour. So are there any questions on the kinetics?
Participants, if you have any questions, you can raise the questions or you can type the questions in the chat box.
Uh, Professor, uh,
Yes.
uh, these equations are, as civil engineers, we have not come across these kind of equations, but is there any textbook that we can have a look on so that we can understand it better?
Yes. It's this PhD thesis from Professor Van Breugel from TU Delft from 91. This would be describing the Heimstrack equation, but there is also PhD thesis from Kunders, Professor Kunders, which I didn't put here, which is actually describing, it's 10 years later, I think. Describing also the Heimstrack, but in a 3D implementation, so it's more, let's say, newer. Then you also have from TU Delft, I will write it, Professor Guang Ye, his thesis, which is also 10 years later, is, where am I here? So Professor Ye from TU Delft. And also many PhD students from him also used similar. So from TU Delft and Professor Ye, you will find this kind of equations, exactly. But they still need, they need improvements, what I told you. But at least you will get this explanation of the omegas. Yes, yeah, that's correct. That you will find it best actually in the original PhD thesis of Van Breugel. I think it's available online. He even made a second edition, so you can go for a second edition. But this is also, of course, Scrivener is very active in this field. This I would recommend. Advances in understanding semi-hydration mechanism, and you will see that actually it's mostly this C3S model. But you will see that she also starts to talk about these effects as well. But mostly, yeah, she was more focused on the nucleation and growth mechanisms. Okay, so we have half an hour. I would like to finish this part for the Pozzolanic reactivity before lunch. So I will just continue. So we have this, now we are in a Pozzolanic reaction. So that's a secondary reaction. And if you have here with fly ash, 20% fly ash, if you measure with thermogravimetry the amount of Portlandite, you will see that the Portlandite is being consumed. First is being produced by the Portland cement with these reactions mainly. And then you have a consumption of Portlandite. So this is then consumed by Pozzolanic reaction. So you have the Portlandite plus silicates, amorphous silica is giving CSH. So this is why this is the Pozzolanic reaction. But of course we can have also aluminosilicates. So the best full way to describe this would be also using aluminosilicates, and then you have the cache phase and the IFM phases. For example, monosulfate. And if you want, we can write this in an easier way with cement notation. So the reaction would be CH plus S plus aluminate plus water basically is cache, gives you the cache phase. So it's the, you know, CSH, and it has aluminate, like 5% to 10, I think even you can have inclusion of aluminate, which is even more, you know, when you have aluminate, this phase is even more stronger, more stable, more durable, let's say, than the CSH phase. So already CSH is much better than portlandite. Portlandite is very soluble, thick. It doesn't contribute to strength. It doesn't contribute to refinement of the pore structure. So just this reaction already giving you the CSH is improving the microstructure. So it's making the concrete more durable. So that's why Pozzolanic reaction is very important. You want to deplete portlandite and make CSH, which is much more, it has these nano gel pores. So you have a very high refinement of the pores. But this with aluminate, it's even more durable. And you have IFM phase also here. So this is the Pozzolanic reaction. When you have so reaction of portlandite, secondary reaction. It's a secondary reaction because the primary is the production of portlandite by cement hydration. Then you have a secondary consumption of that portlandite by aluminosilicates. And this reactivity of aluminosilicates, the Pozzolanic reactivity, depends again on water amount, on calcium hydroxide. Of course, if you again have more calcium hydroxide, the more reactive the Pozzolans are. It depends on the alkalinity, so how much alkalis you have. The higher pH, then the easier to dissolve aluminosilicate glasses, for example, in the fly ash. And you have how much of that silicate aluminate is reactive or is soluble in the, you know, glass phase or amorphous or maybe even in crystal. So how much of these phases are really reactive? So you need to know the reactivity of your raw materials, of your Pozzolans. And again, this is a solution surface chemistry interaction where we again have ion adsorption. And again, we can model it by the kinetics, we should know the thermodynamics, how far are we from the equilibrium and what kind of adsorption reactions we have on the surface. This would give us the full fundamental calculation of the reactivity. We are now working on this with atomistic modeling, but there is still a lot of research needed to really get this kind of fundamental research. Nowadays, it's mainly, you know, empirical kinetics to really to model the Pozzolanic reactions. It's mostly empirical models. So how to measure? Now I go a little bit to the methodology for the characterization techniques. So you have three main methods. It's the Chapelle test. This is the French norm. The Frattini test. This is the European norm. And you have the determination of the reactive silica. This is, you know, you are measuring soluble silicates by HCl and KOH solution. This is also a European norm. Probably there are other norms, but I only mentioned the European norms here. So now I go one by one explaining. So the Chapelle test is you may basically make suspension of calcium hydroxide, diluted water, and then you add your SCM, so supplementary cementitious materials. So it's a 1 gram of calcium oxide. It's portlandite, making portlandite. When you put it in water, and you mix it with 1 grams, but in a better modified version of Chapelle, you mix 2 grams of calcium oxide with 1 gram of SCM, and for 16 hours and 90 degrees you are heating this, And then you are measuring the amount of total minus unreacted portlandite. So basically you want to measure how much of the reacted portlandite, which is the total in the initial amount minus the unreacted. And you can measure the unreacted portlandite by acid-base titration. So if you filter this, you can do acid-base titration, and then you can determine how much, because the pH is determined by the amount of portlandite. I mean, yeah, it's an acid base. It's not the pH, it's just the, yeah, when you consume all the portlandite, then the pH goes down, and then you know that you have consumed all the portlandite, and then from the amount of acid you needed to consume all the portlandite, you know how much portlandite you have. So it's just a standard acid-base titration. You are using 0.01 molar HCl. So you know how much volume of 0.1 molar HCl you used. So you know exactly how many protons you added. And then by stoichiometry, you can calculate when you reach the, the equivalence. You see it by the indicator because the pH dropped. Then you know in equivalence how many protons you added. So you know how many portlandite you consumed. And then you can just calculate the amount of portlandite which was consumed, or remaining portlandite. So and then the total minus this unreacted gives you the consumed portlandite actually. And then you know this gives you the reactivity of SEM. So now I go to the second method. This is the Fratini method. Here you are actually using the solubility product. So you are measuring calcium oxide and pH, the OH minus. And if you measure amount of calcium oxide and OH minus, the solubility curve is like this, because you have this, from the KSP, the calcium times the OH minus on square is constant. And this gives you, this constant is plotted here on this curve. So if you have more OH minus, you need to have less calcium oxide. So this is the solubility curve. And you have this, and then in this saturated calcium hydroxide, you are adding your SCM. You can also use Portland cement, but yeah, which basically again gives you saturated calcium hydroxide solution. Yeah, usually we do it with calcium hydroxide, and then for 7-14 you can do it more days at 40 degrees, and you are measuring, analyzing the amount of dissolved calcium and pH. And then you get this point, one of these points, because you measured your OH, you measured your calcium, and then you can have this point here, and then you can see how far away you are from the solubility curve. And the further away you are, the more Pozzolanic it is. If you are above the Pozzolanic, above the solubility curve, then it's not Pozzolanic, it's hydraulic. So you should be below the solubility curve, and the more further away you are from this curve, it gives you like a semi-quantitative comparison between the Pozzolans. And now from Ruben Snellings, he did this screening of the SCMs. So he used the Fratini test, and then you can see different results. For example, even quartz here. Quartz has non-Pozzolanic properties. Then we have Portland cement. And this is here, of course, has no Pozzolanic properties. And then metakaolin, very strong Pozzolanic properties, very far away from the solubility curve. Flash, somewhere here in between. Slag, depends. First was hydraulic, non-Pozzolanic properties, but then at later age, this is 7 days, and then later 28 days, error indicates the 28 days, we have the a little bit of Pozzolanic properties from the slag. initially hydraulic and then later latent hydraulic and then later was pozzolanic. What was it? This is quartz. Okay, so quartz after 7 days, because it's silicium dioxide crystalline, it had no pozzolanic properties, but then at 28 days actually showed pozzolanic properties, because the test is run at 40 degrees for 28 days. You actually have some pozzolanic properties even from quartz. Let's see, with fly ash in decreased, and this one is natural pozzolan, maybe Truss here in Germany, natural pozzolan. We have also with time better pozzolanic property. And then the third method, this is to determine the reactive silicate. So we have the, you can determine, you know, the amount of silicates you have in your solids. For example, using XRF, this is the X-ray fluorescence. It gives you the oxide composition, or you can use wet chemistry and then also get the silicate content of the solids. Then you treat it with HCl or KOH, similar to Chappelle test, but by 100 degrees. And then you determine the amount of insoluble, or actually the amount of soluble, how much was dissolved in the solution, how much silica is dissolved. But or other way around, you can determine the amount of insoluble in the residue. Yes, if you use XRF, you focus on the solid, so you determine the insoluble residue, and then you can calculate the difference is the reactive one. Okay, so I will just just be careful when you use this kind of test. Don't use in high pH. Don't use glass. You should use plastic, because also the glass is dissolving, you know, the silicates. So you should use always plastic. But then don't heat it, yeah. Or you should use the. Yeah, I'm always skeptical, because in the high temperature with alkalis, you will dissolve silicate from the glass. So I don't believe these results. Use Teflon. Yeah, that is also resistant to temperature and to it doesn't dissolve the silicates. So here approach from Provis, John Provis, how to quantify engineering approach, how to quantify reactivity index. So this is the fly ash and slags on glasses, and actually the reactivity is proportional to the surface area. They found out on many results. Packing density also, because now we talk about you know, reactivity index, and the reactivity index is measuring the strength. Druckfestigkeit in German, so this is the compressive strength in megapascal, and the reactivity index. So how much the strength is increased. If you would get the same strength as in the reference without pozzolan, that would give you 1. And then if you have higher, that gives you the pozzolanic reactivity. And they correlated this index. That's why you have the packing density, because it's about the strength, compressive strength. But the reactivity is in the glass amount. So the more glass you have, the most amorphous phase you have in fly ash, the more reactive it is. This is quite known. You should have amorphous fly ash to have more reactive parts. And it also depends on the glass chemistry. And this is interesting. I want to show you the glass chemistry, how to define the glass chemistry. So you have the network builders, which are basically silico-aluminate iron elements. And you have network modifiers, which are alkalis. So in your fly ash, you have alkalis, they are the glass modifiers. And actually the ratio of network builders between the network modifiers and then network builders, this ratio gives you the glass chemistry. So polymerization degree, this can be explained by the polymerization degree. Also like geopolymers, you know, the higher, the more network builders, they are also called network builders, the more of them you have the bigger network, so it's more difficult to dissolve. But the more network modifiers you have, so like alkalis, then it's you have less polymerization degree, so it's more easier to dissolve. This is why this ratio gives you actually the reactivity. Yeah, here is one model we did long time ago. It was in one conference in Japan. You can see actually these are NMR measurements from literature. They are from Norway. Yes, from Norway Institute, and then you can see this is silica fume and this is C3S, and we have this is C3S reaction with silica fume, so you can see this seeding effect, the filler effect, very strong filler effect, and this is the C3S reaction kinetics without silica fume. So when you add silica fume, you increase the surface area, and you have very much this seeding effect. So the nucleation and growth is much faster. This was the question yesterday. So how the fillers, how they speed up the reaction, because we introduced new surface area for nucleation. So basically you could model it fundamentally by nucleation and growth, but it's quite challenging, let's say, but very interesting approach for research to continue. Yeah, with silica fume, if you measure TGA, you will see also how the portlandite is consumed. This is a PhD from our institute. He made like a database of all this with time, different water saturation, different amount of silica fume. This is the amount of silica fume. So if you go to 40% silica fume, which you will never use, of course, in practice, this was just a research. You should not use more than 10% in practice, because it also lowers the rheology. You have high water demand. It's very expensive also. But this was just to see in chemistry how much you need silica fume to fully react, to fully consume portlandite. So you need almost 40% in 56 days. Yeah, this was a model he made. You can see different pore volumes for different replacement ratios, fly ash, silica fume. What is IR1? This is just a silica filler, okay. And then you can see that the porosity, the more the replacement you give, the higher the porosity. If you use non-reactive replacements, but if they are reactive like silica fume, actually the porosity is reducing. But if it's non-reactive, the porosity will increase. This was the main outcome. So it has to be reactive that you don't jeopardize the porosity. Here I would like to, I think we are in lunchtime. We have 10 more minutes, okay. So this I would like to, ethylene is very interesting. I would like to maybe finish with this. So the clays in general, nowadays very hot topic to replace cement with clays, because they are very highly reactive Pozzolans, and they are also highly available. So this makes them very interesting. And here it's not only metacolin. Metacolin is the best, of course. The more metacolin you have, it's the more reactive. But you have other clays from a mica group like illite, and you have smectites. And elites are mixed in mixed clays. You will mostly find elite and metakaolin, maybe some, but smectates are actually, you don't want them because they are expanding clays. So they are very bad for the rheology. If you have montmorillonite or any smectates, which you can determine by XRD, so you don't want smectates. They are terrible. And because they take water, they are expanding. Yeah, many reasons. Mostly rheology reason for the flowability. You don't want them. Micas, yes, micas okay. Elite, muscovite, they are non-expanding, so they are okay, but they are less reactive. Mostly you want metakaolin, but in most of the clays which are highly available, they are mixed clays. So pure metakaolin is very expensive and not so much available, but most of the clays that are available are mixed clays, so you will have mica inside. And mica, why is the reactivity of the micas less than metakaolin? Because metakaolin has this bilayer structure, tetraeder, octaeder. So this is the silica layer, this is the aluminate layer, and this is then reactive. But if you have, because the aluminate layer is exposed directly with the interlayer, but if you have trilayer, because this aluminate layer is then sandwiched with two silicate layers, this is why those clays are much less reactive. Yeah, you can characterize this. We have with XRD, you can see the amorphous content. You can also see the kaolinite content. If you burn too much, you will see also mullite, and mullite is aluminosilicate. It's like a ceramics. If you burn too much, so the calcination, optimal calcination temperature and duration is important. If you burn too much, you will start to get mullite peaks, and you don't want that because mullite is not reactive. So you should not see mullite peaks on your XRD. And here we characterize two different ones. This is the mixed clay with elite, and this is a pure metakaolinite. You can also do TGA analysis. This is I was always, when you have clays, always do XRD and TGA. And with TGA, if it's a pure clay, pure metakaolin, actually you can quantify the amount of kaolinite, because from the mass loss, from the stoichiometry, you know that you have here two molecules of crystal water, two molecules of water, and this is then you know the mass loss and the theoretical mass loss, and if your experimental mass loss is less, just the ratio between these mass losses gives you the mass percentage of metakaolin in your sample. But in the mixed clay, this is a bit more difficult, because then you have also elite, which has the water loss at the higher temperatures. You also have carbonates at higher temperatures, so it's more difficult. But still, I would try to do always this TGA. It gives you this mass loss around 500, gives you some indication on the amount of metakaolinite. Yeah, we also did many studies on metakaolinite and Portland cement. And actually, if you add 30% of metakaolinite with 56 days of reaction with Portland cement, you would have almost complete consumption of Portlandite. So we are maybe a few questions, few minutes, and then we are ready for the lunch break.
Participants, if you have any questions, you can raise the questions.
So this was mostly now experimental, but later we can do the calculation. I will show you, you can calculate how much stoichiometrically, how much, for example, how much SCM or Pozzolan you should put, or metakaolin. It will be example of metakaolin. How much SCM you should put to fully consume portlandite. That will be calculation exercise. Of course, you can also, more practical would be how much would you consume, what would be the portlandite content if you put, I don't know, 5% or 10% of metakaolin. What would be the portlandite content in your cement paste, which you can measure by TGA. And then you can, you can model, you can calibrate your kinetic model for pozzolanic reaction. But that's a bit tricky always because you have, it's a secondary reaction. So you don't know when you are adding actually the pozzolans, you are also having filler effect. Then your production of portlandite is also faster. So you don't know exactly how much portlandite you produce, that you can then calculate how much portlandite you consume. But you can do, I would recommend you to do the reference Portland cement with filler. So if you add, grinded quartz with similar particle size distribution as your SCM, at least you would get some similar kinetics of portlandite production. And then the difference when you have the blended one, then you can see how much, this is the reference, this is the 0 SCM. So if, I don't know, in 56 days you have, I don't know, let's say 23% of portlandite in your paste. And then if in 56 days, if you have 10% metakaolinate, if you have 13% of portlandite, then you can quantify the pozzolanic reaction. The degree of pozzolanic reaction. This is the easiest way to determine the pozzolanic reaction actually in the realistic system, because you really have the, Portland cement with, it's a paste mixture and with SCM, but I would recommend you to do the reference with the filler effect. Also then 10% of the sand, mix it with sand. And then you can really determine the degree of pozzolanic reactivity. Also with time for each of these. For not only 56 days, you can determine for all the time. So you can see how the degree of pozzolanity, the pozzolanic reactivity with time, how it's changing in your Portland cement system. So this would be my recommendation. This is the easiest way. You only need, the TGA, thermogrammetry, do the mixtures. I would also do calorimetry, and then you can get your degree of pozzolanic reaction. And then you can compare it with your model, or you can calibrate your model. And that model I will show you next in how you can very simply, you can do the with mass balance the way we did it yesterday, but now extend